Welcome back. In this video, we're going to follow up with our next example of a quadratic surface, which is called an elliptic paraboloid. This name comes from the fact that the shape of the traces of this surface are ellipses and parabolas. Recall back to our discussion of ellipsoids. The traces of ellipsoids are all ellipses. Do you see a pattern? When we look at the general form of the equation for an elliptical or an elliptic paraboloid, we get that we can actually write the output variable as a function of the input variable. And in this case, we would write x minus h squared divided by a squared plus y minus k squared divided by b squared, and then we'll have some horizontal shift. Go back to your intuition in calculus 1a. If I just give you that the output is a square plus a number, this is a parabola shifted left or right with some scaling factor to make it wider or narrower, and then some vertical shift. This parabola would be in the xz plane. If I cover this one up, I would have a parabola in the yz plane. And then when I combine those parabolas together, I get a parabola, like a bowl-shaped version. And we'll see that as we get through this video. One thing that I want to call out here is in this general equation, we're going to see that the vertex of this paraboloid, the point in the middle, is going to be at coordinates h, k, j. So the x and y coordinates would be h and k, and then the z coordinate would be j. Another thing that I want to call out is notice in this case we have an explicit function where the output variable is given as a function of the inputs x and y. And we said in previous videos this is z equals f of x comma y. In order to start our analysis of this general form, let's go to a specific example. In this case, let's suppose that we were asked to graph an elliptical paraboloid defined by this equation. The first thing that I would do is notice that h here is equal to 0, so there's no horizontal shift in x. K is also equal to 0, so there's no horizontal shift in y. We have some scaling factor in the x paraboloid, where the a factor is 4, the b factor is 2, and then notice there's no shift up or down here. This is 0. Before we start graphing this in Mathematica, we're going to look at the domain, range, and intercept. We already know that since this is a z equals f of x comma y, we're going to use a plot 3D command, not a contour plot. Contour plots are for implicit equations. Plot 3D we'll use for an explicit equation such as the one we have here. This first step in this process is to think about the domain and the range of this function. So we notice that for the function z equals f of x comma y, where we have x squared divided by 4 squared plus y squared divided by 2 squared, there are no limits on x and y. So the domain of this function is the set of all valid inputs, but we see that any x and y will do. No matter what I put in for x and y, I can always evaluate. So the domain is actually all of R2, which is quite exciting. There's no limits here, which is different from an ellipsoid, right? The range of this function is the set of valid outputs, and notice that the x squared divided by 4 squared will always be greater than or equal to 0, and also y squared divided by 2 squared will always be greater than or equal to 0. Then the sum of two non-negative numbers also must be non-negative, and we see the range in this case is going to go from 0 to infinity. It is no coincidence that the j value being 0 corresponds with the absolute minimum. And we're going to talk about that. Later when we talk about maximizing and minimizing, the value of the vertex gives you an absolute min or max depending if the thing is pointing up or down. And that was the comment here, right? When we look at the general form, this vertex is the absolute min or max, and we'll see that we can confirm this using the tricks of calculus in multivariables. Really exciting. It's almost like we can't wait to get to those, right? Oh my God, we're going to get there, I promise. Okay, so here we have the range and the domain. We might choose, when we graph, we might choose to let x be between -5 and 5, y the same, and then z to kind of use this analysis to get that out. Okay, so now that we've done step 1, which was to analyze the domain and range, let's move on to step 2. In step 2, we're looking for the coordinate axes intercepts. So we'll start with what we call the x-intercepts. And to get the x-intercepts, we would set the y and z values to 0. The moment that I have the y and z values equal to 0, I get an equation which looks like x squared divided by 4 squared. And this means that x is equal to 0. And this also means that I have one x-intercept. Notice that this is actually the unique intercept for all 3 axes. So that was a really quick analysis, and we got lucky there. So we have infinite domain inputs. We have a single intercept. We can go on to study the traces. We said that we had 3 very common traces, but the xy trace in this case, which corresponds to setting z equal to 0, is almost useless in the sense that when we look at the equation 0 equals x squared divided by 4 squared plus y squared divided by 2 squared, we all already know, based on the fact that this is going to be intercept, the only way that this happens is x equals 0 and y equals 0. So this trace is actually a single point. However, we can do a trace in the same direction by taking a general z equals z naught. And in our case, why don't we take the constant 4? So in order to look at this trace, we're going to look at the intersection of the plane. This is now going to be a plane that is parallel to the xy axis, xy plane, excuse me, at the height 4. So the moment we see this, this is going to mean 4 is equal to x squared divided by 4 squared plus y squared divided by 2 squared. And then we can go ahead and divide by 4 on both sides, and this would be 1 over x squared. And then here, this would be 16 times 4 plus y over 4 times 4, which of course when we look at this is going to be x squared over 64 plus y squared over 16. And of course we can see that this is actually an ellipse, aka elliptic paraboloid. There's the ellipse trace. So this is going to be x squared plus y squared over 4 squared. Remember that this trace was at height 4. We could use a parametric equation to get this trace. In the x coordinate, we're going to have a 8 cosine of t. This is not moved left or right by h, so we don't need a shift. This would be 4 times sine of t. Again, we're going to have no shift, so there's the ellipse there. And then remember that the z value was at 4. So now this trace is going to be given by the vector valued equation here, and this is going to be what we call a trace in this particular plane. We can also look at what we would say is the xz trace, and the xz trace will come from setting y equals 0. The moment I've set y equals 0, we have that z is equal to x squared divided by 4 squared. And this is going to be a parabola in the xz plane. So when we look at the vector valued equation, perhaps we would just set x equal to t. So here the x would be t, the y is 0, and if I said x equal to t, what is z? Well, z is this x value t squared divided by 4 squared. And so this is going to be the trace in the xz plane. And then similarly, we can look at the yz trace. And the yz trace will be come from setting x equal to 0. And this will immediately imply that z is equal to y squared divided by 2 squared. But if I were to make this happen, this is going to be a vector valued equation. So maybe we call this one like R2 of t, and we'll call this one R3 of t. Okay, my x value is going to be 0. My y, I'll use a dummy variable t. And then my z would be this dummy variable t over 2 squared, because that's the relationship between the two of them. And this will be in the yz plane. Notice these are both parabolas, right? This is a parabola in z and x. This is a parabola in z and y. So indeed, we have traces that are ellipses and then parabolas. Let's switch over to Mathematica and actually graph this and superimpose the traces on top of it. Here we go. Here we are in Mathematica. We said that we were going to define a function. We'll call it f. When we're defining a function and we don't want to have x and y be a specific value, we use these underscores, and then we use the delayed assignment : equals. And in this case, we had a specific function. We had x squared divided by, so here we go, 4 squared, and we'll see how to generalize this in a sec. And then we had our y squared divided by 2 squared. And let's go ahead and suppress that. So now my f function is a specific output in terms of my two inputs. Because I'm going to plot this and it's explicit, this is plot 3D rather than contour plot 3D. So I'm going to go ahead and say end plot 3D command. Again, notice that I'm lining up the first letter of the word plot with the end bracket in plot, and this is for debugging. Well, what do I want to plot? I want to plot the function f of x comma y. This is where the domain would come in helpful. Remember that we have all x's and y's are valid, so maybe we choose to go from -5 to 5 in my x, and we'll also go from -5 to 5 in my y. I can let Mathematica automatically calculate the range. So right now I'm ready to evaluate this plot command. Here we go. Okay, notice that I don't really get a good representation of the surface. It's not wide enough, right? So one thing that I could do is actually determine the range. So I'm going to tell Mathematica, hey, Mathematica, I want you to do what I tell you, not me to do what you tell me. So I'm going to tell Mathematica that I want to go from like -2 on the lower end, and then maybe I'll go up to like 25 on the upper end. Let's try 10. Still not good. Let's try 4. Okay, that's a little bit better. One of the issues, you might not know this, but these scaling factors are really making things tough. So why don't we go to like 10 and 10, and then we'll also go to 10 and 10. And I actually am doing this on purpose. I could have planned this all out. In fact, I did before I started this video. I want you to see that some of this is guess and check, and there's no way around that. Okay, so here we have this initial representation of our elliptic paraboloid. Perhaps we want to increase the size of this, so I might say image size, and let's say large, shall we? That's much better, isn't it? Okay, do you see how Mathematica is graphing my image, but it's filling this in with like a gray plane? That's because at this particular value in the domain, the range doesn't have outputs. So what we do is we write this, to get rid of that, you can write clipping style none, I believe, and that will delete that extra gray plane. And then of course I like to say plot style, and perhaps I want to do directive, and let's do something exotic. Let's do red in this video, shall we? So there's red, and then let's turn off the mesh. So let's say mesh false. Okay, so now we've got this kind of elliptic paraboloid. You see it? Yeah, and then this is where it would be useful to actually increase the range. Maybe we'll increase it to 10. Okay. And that gives you a sense of what the elliptic paraboloid looks like. These scaling factors, if you change them, let's change both of them to 1 and see what happens. Yeah, isn't that exciting? This thing is very opaque. Opaque means I can't see through it. So I'm going to decrease the opacity, and we'll decrease it to, my favorite is 20%. So now I can see through it, right? Ooh, that's too see-through. Let's go to 0.4. Okay. And then let's force the axis to go right through the origin. So we'll say, please put the center of my axes through the point 0, 0, 0. Okay, there it is. And then we had these different traces, right? So we want to graph the traces here. We had 3 of them that we did in our paper and pencil analysis. And we'll do all 3 in this video. And then we're going to end, and we'll do the rest of our quadratic surfaces in class. So here we have show, and we're going to combine this with a plot, parametric plot, and this is going to be in 3D. Let's open and close brackets. The first parametric plot we said was going to be an ellipse, and we said that the radius of the ellipse was going to be 4 because this was 4. This is where I might generalize. Let's call this thing A, and we'll set A equal to 4 for starters, and then we'll put this down here as A, and this is B. So B was 2 for starters, right? And the reason that we're going to do this is in the parametric plot, we said that this was going to be A times cosine of t, B times sine of t, and then the plane that we were looking at is the z equal 4 plane. So go back to the pen and paper analysis that we talked about, and we'll let t go from 0 to 2 pi. Okay. Let's see. What is going on? Those should actually be intersecting with each other in the exact points. What's happening here? A is 4, B is 2. My ellipses. That doesn't look that the parametric plot looks like it's inside the ellipse, so I'm not sure what's going on here. Why is this messing up, huh? Oh, of course. We said that in the z equals 4 plane, this thing was going to be 8, and this thing was going to be 4. Remember that analysis? Yeah, you see it? Yeah, so this was just a silly mistake on my part. And we could go ahead and do plot style on this one. So here we had plot style, and we're going to say that this is going to be bright blue. So it already is blue, yeah. Okay, so there's my ellipse. And then we had 2 other parametric plots. We had our xz trace and our yz trace. Xz trace comes from setting y equal to 0, and we were going to call the t parameter t, and then this was t squared divided by what? I think it was something like 4 squared, right? And then of course here we would want t to go from, like, I don't know, -4 to 4. Doesn't look like that's far enough. So there's, you see that the axis there? Maybe we say the same t here. X is going to be t. So let's go from -10 to 10. There we go. -10 to 10. Ah, there we go. Do you see it? So, and let's turn this to green just to make it clear where the trace is. So there's the trace there. So I have an ellipse, and then in the xz plane I have a parabola. And then we also saw that we have a parabola in the yz plane. So here we said the yz plane came from setting x equal to 0. This is going to be t, and then this was going to be 2. Look back at your notes if you want to see more on this. Let's turn the YZ trace to red. Red's not a great color, is it? Should we try yellow? Yeah, there it is. So those are my 3 traces. And I could actually show you specifically that these traces correlate with the intersection in the plane. So I'll do contour plot 3D. Let's do the z equals 4 plane. So z equal to 4. And then we'll do the same x, y, and z value. So this is -10 to 10. Y would go from -10 to 10. And then z would go from, well, what was the, what was the range in z? The range in z that I said was going to be my output was -2 to 10. So here we say -2 to 10. See it? And then, of course, let's do contour style. And then we'll do directive. And we'll go blue. And we'll have the same thing. We'll go opacity. I think we said like 20% was something that I keep using. And then we'll also turn mesh off. Yep. So the red, you see where the red, it's kind of hard to see this here. You see where the red elliptic paraboloid intersects with the blue plane at z equals 4? That intersection is the trace that we've graphed there. Pretty amazing, right? Don't worry if you're not understanding this fully. Remember, one of my favorite quotes about math is, you never really understand math, you just get used to it. Okay, we're done with this lesson formally in videos. We'll move on to the next lesson very soon, and I'll see you in class to practice the last few quadratic surfaces. Great work, y'all. Keep it up. See ya.